In this video, we're going to talk about integrals, a kind of integrals called improper integrals. So the idea is the following. So suppose I have a function. So in this case, I'm looking at the function f of x equals 1 over x squared. And suppose I'm interested in the area under the function. So typically, you take a finite interval, and because it's a finite interval, the area is going to be finite. However, in this case, I'm interested in the area under the curve, so the entire curve that's to the right of x equals 1. So over the interval from 1 to infinity, right? So it looks like this area is infinite, but we'll see that something surprising is going to happen. So the improper integral we're going to think of is so we're going to integrate from 1 to infinity the function 1 over x squared dx. So the idea of trying to make sense of what this is supposed to be is the following. So suppose instead of doing the infinite interval, I chop it up into a finite interval, so from 1 to b, and so this is definitely going to be a finite area, and I'm going to keep moving b to the right until it goes to infinity. And then, so as I move b to the right, going to infinity, then I'll cover this entire shaded region. So the way I'm going to compute it is to take a limit to the limit as b goes to infinity of the integral from 1 to b 1 over x squared dx. Right, so this is a finite integral, and then I'm going to increasing the finite integral until b goes to infinity, and then see what happens to this quantity. Okay, so this integral I just evaluate like normal. Right, so I evaluate the integral first, so I rewrite it. So 1 over x squared is the same thing as x to the minus 2. Then I find the antiderivative. So I use the power rule. Right, so I increase the exponent by 1 divided by the exponent. And then now I plug in b and 1. So this is limit as b goes to infinity. So plugging in b first, I get minus 1 over b. And then plugging in 1, I get minus 1. So this expression is 1 minus 1 over b. And then now I take the result of the integral, right? So the area from 1 to b is going to be 1 minus 1 over b, and then I take the limit as b goes to infinity. So as b gets larger and larger, this fraction gets smaller and smaller until it goes to 0, and so this limit, so as b goes to infinity, this will go to 0, so we're just left with 1. And so what this is saying is that as b goes to infinity, this area is increasing, slowly increasing, but it's increasing and then approaching 1. And so even though the extent of the interval is infinite, the actual shaded region has a finite area. So intuitively, the way you should think about this is that as we move b to the right, it's contributing some additional area, but the contribution is so small that the total is still finite. So this is how you should interpret this integral. Okay, so now that we've seen an example of an improper integral, let's discuss the different kinds of improper integrals you can have over the different kinds of infinite intervals. Okay, so there are 3 kinds of infinite intervals, and then each kind has a different improper integral associated to it. Right, so the first kind is what we saw. Right, so suppose you have an integral where the right side goes to infinity. The second kind is if you have an interval where the left side goes to minus infinity, and you can have an interval where both the left and the right side goes to infinity. Okay, so then let's see what kind of region you might have. So you can have, say, your function f of x should be like this, and say a is some point here. And so this is sort of the situation that we did in the example above. Right, so the region goes to infinity to the right side. Okay, so let's sketch the second situation. So suppose you have, again, your function f of x. Now suppose you're interested in an area that extends to infinity to the left. So in the second case, you're interested in this region here. So again, going to infinity. And then in the third case, we're interested in the region over the entire x-axis. So the entire region over the entire function. Okay, so let's take a look at how to set up the integral in each case. Right, so this is the case where the left endpoint is fixed, and then the right endpoint goes to infinity. So the way we compute it is exactly what we did above. So then you fix the right endpoint, and then you slowly let it go to infinity, and you compute it using the limit as b goes to infinity of the integral from a to b f of x dx. Then in the second case, do something similar, right? So then you fix the left endpoint, and then you let it go to minus infinity by taking a limit. So the improper integral is going to look like the integral from minus infinity to b. And then the way it's computed is to take the limit as a goes to minus infinity, integrating from a to b f of x dx. Right, so you compute this integral first, and then you take the limit as a goes to minus infinity. And then finally, when you're integrating over the entire x-axis, so in this case, because both the left side and the right side are going to infinity, what you actually have to do is to actually split it into two integrals. So suppose I split it down the middle somewhere, any point, you can use any point, and you have a right endpoint and a left endpoint, and each of these goes to infinity. So this side goes to minus infinity, this side goes to positive infinity, and you split it up into two separate integrals. So the improper integral looks like the integral from minus infinity to infinity f of x dx, but then the way you calculate it again is as two separate integrals. Right, so first on the left side, you go from a to c, f of x dx. So this is the left side, and then you take the limit as a goes to minus infinity, and then you do the right side separately. So this part, you integrate from c to b, f of x dx, and finally you'll take this limit as b goes to infinity. So the double infinite integral has to be computed as two separate integrals, one of the first kind and then the other of the second kind. So let me make this note. So doubly infinite integrals must be computed as two separate integrals in this way.